Hi folks, hope you all be well. I am vicentefachina and I work in the oil and gas industry. The reason why the number 2 in the title is that this is an upgrade over a presentation I did in Brazil in December 24. I begin with a provocative question. Might this be a rebirth of the oil and gas sector in this century and beyond? This is the summary, and soon you'll see why the acronym Otec, Ocean Thermal Energy Conversion, does hold true here as well. This is the classic Otec concept, which is more than a century old, a topside platform that utilizes a Rankine power cycle that taps into the temperature difference between the surface and the deep sea waters. Warm surface seawater heats up a working fluid to do work in a power steam turbine. Cold bottom seawater cools down the working fluid in a condenser. The condensed working fluid then goes for exchanging heat with the warm surface seawater, and the cycle repeats itself. Nevertheless, there are serious drawbacks of the classic OTEC concept. You see what a topside installation negatively entails. Big water pipes in open sea, unstable offshore environment, wave storms, heat source dependent on latitude, biological impacts. Besides small energy efficiency due to the small temperature difference between the surface and deep sea waters. Still, OTEC is a baseload renewable power route with expected capacity factor above 90%. Now, the deep OTEC concept. By the very definition, no topside installation with all such positive points, which are just the opposite as to the prior slide. No big water pipes in the open sea, stable environment, no wave storms, heat source independent on latitude, biological impacts minimized, very few fish. Besides, much larger energy efficiency because the heat source is not warm surface seawater. And here's the catch. The heat source lies beneath the seabed, and the heat sink is all around stable cold seawater, for which the acronym Otec does hold true, also called deep sea flow geothermal energy. The heat source is magma between 12 and 20 kilometers deep into the Earth crust beneath seabed. This is the diamond risk approach that utilizes four risk dimensions: innovation, technology, complexity, and lead time. The higher the number, the, the higher the risk in each dimension. So the larger the diamond area, the higher the overall risk. For instance, on innovation, current product, the lower risk, it's 1. It's a product revision, somewhat risky, 2. New product, the higher risk, number 3. This illustrates a high-level business risk assessment for deep Otec or deep seafloor geothermal, against which I compare with deep onshore geothermal. In the innovation dimension for the deep onshore geothermal, this deals with a product revision because there has been onshore geothermal for more than a century. For deep Otec or deep seafloor geothermal, this deals with a new product indeed, because it has never been done. Well, both routes have high risks, and deep Otec even higher. So, why deep Otec though? The earth crust beneath seabed is thinner than onshore for reaching out deep hot sources. Deep seafloor geothermal has no problem with water availability, of course. Deep seafloor geothermal can produce other products or services besides electricity, and the oil and gas industry can make it come true. This is a schematic of a Rankine power cycle for simulating some relevant quantities. For instance, dispatching 500 megawatt electricity require 615 kilo per second steam flow at 300 degrees Celsius, 60 bar pressure, and 15 meter per second steam flow velocity, which entail a 1.4 meter diameter water pipe. In addition, here you see a thermoelectric converter to tap into some of the heat sink, so to reach about 31% energy efficiency, without which it is about 26%. Here you see either a heat battery or a heat exchanger, by which you can use a binary circuit, proper clean steam as a second working fluid to protect the power package from the raw steam which is generated in the heat source in the first circuit. And here you can see what I call a sanity check for the model and simulation actually come true in the face of reality in the pilot tests. It's a ratio in the numerator, the gross electric outlet, and in the denominator, the heat inlet. This illustrates a design operation point for the power engine shown in the prior slide. This is a temperature enthalpy plot, where the red dot shows a design operation point which might be superheated steam at 60 bar and 300 degrees Celsius. And this shows two curves. The superior, the red one, is a unit heat energy temperature plot, which is all the available unit heat that enters the power cycle from the working fluid exchanging heat with the heat source. The inferior, the blue one, is a unit electricity temperature plot, where the red dot shows the unit electricity outlet, about 800 kilojoule per kilo steam. In the left, I show the model for both curves. This is a product portfolio for Otec. Beyond electricity, Otec might deliver other utilities. In the diagonal, you see some utility segmentation. And in the off-diagonal, you see their networks with the other utilities, with supplies in the horizontal cells and demands in the vertical cells. For instance, Otec supplies electricity for all the other utilities. The hydrogen plant receives electricity from Otec and hydrogen from an electrolysis plant, and it delivers hydrogen to end users. In addition, I marked some clusters. These are clusters for water supply, either potable water or seawater air conditioning, and a cluster to supply either hydrogen or oxygen. That's all, folks. Now, the conclusions on the essentials. To connect the expertise of oil and gas and geothermal energy badly needed. To use decommissioned oil and gas wells for pilot deployments. To drill much deeper from about 12 kilometers towards 20 kilometers deep beneath seabed. And some reflections. Why did the oil and gas industry go for deep offshore drilling? What is the oil and gas industry to rebirth for in this century? Here there are some YouTube references. Thank you very much for your attention.